Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll look at the cardinality of a set. So at its most basic level, cardinality just tells us how many elements are in a set. So if we have the set A is 1, 2, 3, 4, the cardinality of A is just 4. That's nice and easy. But what about a set like B, which is the natural numbers? Now, I just want to point out that some textbooks include 0 as a natural number, some don't. There's not 100% agreement amongst mathematicians. When I say natural numbers, I'm talking about the set of all positive integers, 1, 2, 3, and so on. Now, this is clearly an infinite set. There are infinitely many natural numbers, just as there are infinitely many real numbers. So real numbers, of course, includes all the natural numbers, but then we've got to include fractions like a half, a third. We've got to include negative numbers like -7. We've got to include irrational numbers like square root of 3, square root of 5. Clearly, that's an infinite set. But which of these has larger cardinality? See, that is a question that perplexes a lot of people. Both of these sets are infinite, but at a common sense level, we'd say, well, clearly this contains more elements than this. And that's where cardinality gets tricky. It's very easy for finite sets, but a lot harder for infinite sets to determine which set has greater cardinality. Now, it's been known for a long time that there are different types of infinity. It's also been known that the usual rules of less than, greater than don't apply when you're talking about infinite quantities. So these are both infinite, but to someone who's a mathematician, this set would have a greater cardinality. There are more real numbers than that. So to distinguish between two types of infinity, we say the cardinality of the natural numbers is this symbol here, aleph naught, and the cardinality of the real numbers is aleph 1. So a set whose cardinality is finite or equal to aleph naught is said to be countable, otherwise it's uncountable. So we say that these two sets are countable and this set is uncountable. Now, the continuum hypothesis is a very interesting theory that says there's no set that has cardinality more than this but less than this. Now, that is just a hypothesis. It hasn't been proved, and interestingly, it's been shown you can't prove it using the ZFC axioms for set theory, which tends to be the most popular amongst mathematicians. All right, let's look further at this concept of being countable. So if we have infinite sets, how do we decide whether they're countable or not countable? We're going to use this rule here. Two sets have the same cardinality if there exists a bijection between them. So here we have two sets with cardinality 2. We can easily come up with a bijection like this. This is a bijective function. It's onto, it's 1-to-1. Of course, for these two sets here, they have different cardinalities. This one has cardinality 3, this is cardinality 2. There is no such bijection that can be drawn. It is impossible. Of course, remember that a bijection is just a 1-to-1 correspondence between elements of the first and elements of the second set. We can't possibly have a 1-to-1 correspondence when there are more elements in the first set. So we're going to exploit this to determine whether or not sets are countable. So let's consider this set here. This is the natural numbers adjoined with the number half. So this contains all the natural numbers, but we're also including a half. So it's the set half, 1, 2, 3, and so on. So it's logical to think that this has a greater cardinality than that of the natural numbers. I mean, we have all the natural numbers and we have added one more. But to determine if that's actually true, we see if a bijection can be created. Now, we can create one between this set and the set of natural numbers. So basically, a set is countable if you can enumerate its elements. You can say this is like element 1, and this is element 2, this is element 3, and so on. So if we want a bijection, we want something that maps a half to 1, maps 1 to 2, it maps 2 to 3, and so on. Now we can come up with such a bijection fairly easily. Now this here is a function. It is a hybrid function because it does something slightly differently for this element than for the rest of the elements, but it is a bijection nonetheless. It is 1 to 1 and it is onto. We could easily find an inverse for this function. We can see though, the point is we can line up elements of this set with elements of the natural numbers. There is a 1-to-1 correspondence, and so they have the same cardinality. Even though we might think that this has more elements than the natural numbers, I guess we're essentially saying that this set here and the set of natural numbers, they are of cardinality that's the same type of infinity. So because such a bijection exists, this set here is countable. And if we believe the continuum hypothesis, this cardinality is much less than the cardinality of real numbers. Let's look at another example. So we know that the real numbers have greater cardinality than that of the naturals, but what if I get rid of like half of them? What if I get rid of all the negative numbers and only consider all the positive real numbers? What would the cardinality of this be? Would it be the same type of infinity as the natural numbers or the same type as the real numbers? So to do that, we look for a bijection. So what we're actually going to do here is look for a function that maps positive real numbers to the real numbers. And there are many such functions. One obvious one that gets used a lot is lnx. So the input here has to be a positive real number. You can't input into the natural log 0 or a negative number. And if you do that, you get some number y that is another real number. So we found a function that maps this set to this set. We just don't know yet whether or not it's a bijection. So let's check whether it's onto and 1-to-1. Now this map is clearly onto because every y value, every real number gets mapped to. We can simply raise e to the power of each side. Now e to the power of ln x is just x, and e to the power of y we just write as that. In other words, if I have a real number y, I can always find which number mapped to it. The number that mapped to it is just e to the power of that value of y. Alternatively, you might sketch a graph of this and you will see that it has full range. The range of this function ln x is the whole real numbers. Now what about 1-to-1? So remember, we want to check whether or not different inputs lead to different outputs. So let's consider the case where two inputs, x1 and x2, map to the same real number. That means they'll be equal. So I can just raise e to the power of each side and I get x1 equals x2. In other words, if two inputs map to the same output, those two inputs must be the same. In this function here, different inputs always yield different outputs. This function, which is fx equals ln x, it is both 1-to-1 and onto. It is a bijective function. It has a clear inverse, fx equals e to the x. Now, because there is a bijective function or a bijection from this set to this set, they must have the same cardinality. So that means that the positive real numbers has a greater cardinality than aleph naught, which is the cardinality of the real numbers. Its cardinality is actually aleph 1. Which is the same as the real numbers. So the real numbers and the positive real numbers have the same cardinality. That might be hard to understand. You clearly think there are more in this set than in this set, But again, less than, greater than doesn't have the same meaning when we're dealing with infinite quantities. These two sets have the same cardinality. They're both infinite. They're both uncountable sets, but their cardinality is like the same type of infinity. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.